Before we really talk about logarithms, I'm going to talk a bit about exponents. So I'm going to trying to go a little bit faster over this because I typically expect this to be more grade school education, like we're talking about like high school. So I would hope that you have some understanding of some of these things, but at the same time, it's okay. I'm going to do a bit of overview. So recall, for any real number, x that's not equal to 0, and what we call the exponent or power, and exponent or power n, which is going to be a real number, rewrite x to the power of n, where we call x the base of the exponent. So these two are rather important for me to bring up, just for the sake of discussion here, is that we're going to use this terminology of a base and an exponent very often. So often you'll read this as x raised to the power or exponent of n, or you'd say x to the power of n. So you might ask, Dan, what does this mean? Well, I'll just give you an intuition when it comes to just integers, because this will work well enough for our discussions here. If exponent n is an integer, then what x to the power of n means is it's x times x times x times all the way where we have n of these. So we have a product of n x's. Note that if you're wondering, as an aside, these are a couple things to keep in mind, is that x to the power of 0 is equal to 1, and x to the minus n is equal to 1 over x to the power of n. So now there's a variety of different properties that exponents have, and you're going to see that these are going to translate very naturally to logarithms. So just for the sake of consistency, I'm just going to let real numbers x and y not equal 0, and m and n be real numbers. So these are some short properties. So this is going to be a list of properties that exponents have. So some of these I may have mentioned in the past, but here's first property is the product property. So the product property works like this. So if you have a product where the two terms you are multiplying have the same base, you can add them. So x to the m, x to the n is no different than me writing x to the m plus n. Just as an example, 2 squared plus 2 to the power of 1 is equal to 2 to the power of 2 plus 1, which is equal to 2 cubed, which is equal to 8. That's a very liberal use of equal signs, okay? So you can check this very quickly by noticing, you can check this computation. Notice that 2 squared is 4, and 2 to the 1 is just 2, so it's 4 times 2, which is just equal to 8. But also you can use it in a different way too. So for example, if I have a larger exponent, I can also decompose the number into multiple terms using this property. So this is another thing to keep in mind about this. So it doesn't just go like one direction. You can unwind this. So if I know 2 cubed, well, 2 cubed is the same as writing 2 to the power of 2 plus 1. So I can do the same thing here. So for example, if I have 2 to the power of 8, if I want to do a simpler calculation here of what 2 to the power of 8 is, I can go 2 to the power of 4 plus 4, because that sums up to 8. But what is this? Well, it says that I can express a sum like this as a product of two of the same base with those exponents, right? So it's 2 to the power 4 times 2 to the power 4. But 2 to the power 4 is just 16, so this is 16 times 16, which if you know your powers of 2, this would be 256. But that's okay. So that's just that's just how you can use this product property. So I'm not going to prove this property here. I'll give you an example of a proof for one of these properties as we come up. So the big thing that I really want you to notice here is that if you have two of the same base, you add the exponents. So just take note of the fact that you're adding the exponents. This is important. So just take note of that. Now, the next thing I'm going to talk about is the quotient property. You're going to see that this is going to be like, because it's natural, because if you were doing the reverse operation of multiplication is division, because you can express division in terms of multiplication. But I'm not going to go too much into detail about that here. It's a whole other fun discussion. Like you just look at product, like if I have x to the m and x to the n, it's no different than me writing x to the m over x, sort of multiplying it by, so I have x to the m times 1 over x to the n, for example. Notice that this would just be like if I divided x to the m divided by x to the n. So this is what I mean. So this shouldn't surprise you that if you know that 1 over a something, if it's x to the n, for example, you know that's x to the power of minus n, right? So it shouldn't be very surprising that instead of adding, you end up subtracting. You get a difference. So we have the quotient property. So it's x to the m over x to the n. Well, this is x to the m minus n. Just as a quick example. Like I said, a lot of this stuff's pretty basic, but it's clever and nice. So if I have 2 to the power of 8 divided by 2 to the power of 5, this means it's 2 to the power of 8 minus 5, which is equal to 2 cubed, which is equal to 8. I encourage you to double check that calculation. So, next, let's talk about the power property. So this is number 2. Let's have number 3. The power property. So if you have something being exponentiated like this, x to the m, and you have outside of here, it's getting exponentiated again through what is a product of exponents like this, naturally you'd see that it's actually going to be expressed as a product, not a sum. So if you have this, x to the m, and you raise this to n, it should be x to the m times n. And if you're thinking about this in terms of integers, this shouldn't be very surprising to you. If you actually think about this carefully, notice that if you just put any other number here where x to the m is, like say that's a. Well, you would say that that is just a to the n. And you know, if we think of the exponent as an integer, so just this intuition is very natural if you're thinking about an integer, although this property is much more general than this. You can imagine it's a written out n times, right? A product of a n times. Well, if each one of them is x to the m, instead of just being written as a, well, you have x to the m written out n times, right? So you can use, in that case, if we're talking about this, we can use the product property. And you'll notice that all I'm doing is I'm just summing up I'm taking x to the m and I'm doing this n times. So I'm summing up m n times, which is m times n. That's pretty cute, right? So just as a quick example, 2 cubed raised to the power of 4 is 2 to the power of 3 times 4, which is 2 to the power of 12, which if you're curious about what that is, that's 4,096. Double check that calculation. Now, another one that has come up before, or at least is something that you could discuss, is power of a product property. So this is the one that we are using. We actually use this for when we talk about properties of big O. I use this property explicitly. So if I have x times y raised to the m, this is no different than writing x to the power of m times y to the power of m. So notice the parentheses. It's x times y raised to the power of m. Now you might ask, Dan, how is that the case? Well, let's think about it. You have x times y times x times y times x times y times x times y. And if m is an integer, you will see quite clearly that this is written out m times, right? Well, all you do is, because multiplication is commutative, I could just simply arrange all of the x's together and all the y's together, and then I can just group them like that. And then I have m many x's and m many y's, and you'd use this product property I have over here on the left board, and you just sum them up, right? You can just view it that way. That's one way you could go about this. There's several other ways you can. But that's one natural way you can look at this if m is an integer. So just as a quick example of what I mean by this, if I have 2 times 3 squared, what I'm saying is it's 2 cubed times 3, sorry, 2 squared times 3 squared, I wrote down cubes, is 4 times 9, which is equal to 36. And like I said, you can always expand the terms here to see what I mean. So if it's 2 times 3 squared, well, that's 2 times 3 times 2 times 3. Well, this is the same as me writing 2 times 3 times 2 times 3 like this. Then on top of that, you could just simply rearrange this so all the 2's are together and then all the 3's are together. So 2 times 2, 3 times 3. But this is just 2 squared times 3 squared. Boom. Is that nice? Okay. Now, one thing I also want to bring up, just as a remark, and I'll have more discussion about this in the notes, is that very often when we do we perform algebraic operations. So for example, you know when sometimes you add numbers to both sides of an equation, or you take a difference on both sides of the equation, or you divide by both sides, or you take logarithms of both sides, which will be relevant here. You might ask, Dan, what does that even mean? So like, what does it mean for taking logarithms to both sides? Well, here's the first thing I really want you to think about, is that if we have it where 2 elements are equal to one another, well, if I apply them to some function, then it has to be, because, just remember we talked about our machine we had earlier? So we imagine the function as a machine. So if I give you the input and I spits out output, right? If I give you the same input, it should output the same number, right? So if I have 2 elements that are the same, they're equal to each other, then the machine, the function, should output the same result, right? So naturally, if I have 2 things that are equal to each other, if I apply an operation such as a logarithm to both of the sides of the equation, which has both the same elements on both sides, they're equal to each other, then it should be that the result of this should be, if I apply logarithms, so if I put I put those 2 elements as input to the logarithmic function, then they should have the same value. That's because if I have 2 elements a and b, if they're equal to each other, then log base b of a, I shouldn't give a base yet. Log a is equal to log b, and I haven't defined what a logarithm is quite to this stage, although I have done so in previous sessions, which is why I'm saying this. And this is true in general settings, so this is because a function is what we call well-defined. So I have some more discussion about this in the notes. I just thought it would be an interesting thing to discuss here. So you might say, Dan, these are rather interesting things to know about exponents. Well, let's start talking about what a logarithm is, seeing as I started talking about those. So let's start talking about that. Now, I gave you a list of properties. Now, there's actually a complementary list of properties that logarithms have that should it shouldn't surprise you. I know I'm saying that a lot today because I think that a lot of this is review, but it doesn't necessarily have to be. This may be your first time being exposed to this. That's okay too. Everybody is welcome. If you have any questions, just let me know. So let there be positive reals. So these are going to be positive real numbers. X, Y, and B, where B is not equal to 1. See why in a moment why it may not make a whole lot of sense for B to be equal to 1. Then there are the following properties for a logarithm. Following properties for logarithms. Now, just as a quick reminder, what a logarithm is that I normally, when we exponentiate, we have a number, a base of the exponent raised to some power, and we get a result. That's the result of exponentiation. So I'm going to ask the inverted question. So imagine I give you, let's go b to the, suppose I give you let's go b to the, I don't want to use x over here because we're going to use x and y in specific ways. But I'll just use, let's go b to the d is equal to x. Now, in exponentiation, what you do is you take b and you raise it to the power of d, and you get, as a result of the exponentiation, x. Now, what I would like to know is if I give you the base, b, and I give you x, what is d? I want to know what that is. That's what the logarithmic function is. That's what logarithms are. So the way I would re-express this in terms of a logarithm is I would write log base b of x is equal to d. So that's the definition of a logarithm in about a minute. So let's talk about some properties now. So you can see that there's a close relationship logarithms have with exponentiation. Just the question now is, instead of it being what's the result of raising b to the exponent d, I want to know what d is. So here's some properties, and you're going to see that they're going to be somewhat related to the things we just talked about. So a product rule. So this is going to be the product rule of logarithms. So I'm just going to call it the product rule just for the sake of brevity here. But I mean the product rule of logarithms, or product law of logarithms. This is log base b of x times y is equal to log base b of x plus log base b of y. Now, if you think about this very carefully, if you look at this statement, you notice I have log base b of x is equal to d. So this is the result. This is like the expected, sorry, I'm getting very excited here. The expected result of log base b of x. So what does this mean? This means b to the something is equal to x. Well, if I give you that b to the something is equal to x times y, well, let's think about it. I have b to the something is equal to x times y. Well, we have actually looked at something like this before. It should remind you of the product rule, the product property of exponents. So if I have some number, and this is the result of the exponentiation, well, what does it mean? B to the something is equal to x times y. Well, think about this carefully. It would be b to the something is equal to x. So that would be whatever x is. And then you have b to the something is equal to y, right? But well, that's the product, right? Like, I'm just trying to give you an intuition behind these, because I'm not going to prove all of these for you up here, because like I said, most of this I consider review for the discussion that we're having. But I'm trying to give you some intuition behind this. So So the point here is that if you have a product like this, we know that if we have a product and we're trying to express it in terms of exponentiation, we already know that when you have two of the same base, notice that these are the same bases. So this is the same base here. So it's b to the something is equal to x times y, right? So what I'm saying is, if they're the same base, you know that if you multiply, you should expect that their exponents sum to each other. Like it's a sum, as you see right here. So if you're not sure about this, just look at this definition carefully and try to put this in place for the rule I have here. So that's the first one. Naturally, if I give you the quotient rule for a logarithm, well, you should expect that log base b of x over y, so x divided by y, it should be a difference, right? Just like how we took the exponents and we had a difference as opposed to an addition. That's the quotient property or quotient law of logarithms or quotient rule of logarithms. Another one that's helpful to be aware of is the power rule of logarithms. Many, many properties can be derived from this one specifically, but these two are also very helpful. The power rule of logarithms. So this is where if I have log base b of x to the y, so notice that this is all together. It's x to the power of y. Well, if you look at this, it's x happening, it's like x, whatever the result of this is, but it's done y times, right? So you would have y times log base b of x. So I thought, before I get too ahead of myself, I'm actually going to prove this property here for you. So if you're wondering offhand, Dan, where did this come from? Let's do the proof here. So I'm going to we're going to prove number 3. And to do this, I'm going to use the definition of a logarithm. So let z equal log base b of x. And I'm going to use the variables as I've defined them up here. So note that the theorem statement is going to be more precisely stated in the notes, but the variables should be the same ones I have up here. So let z be log base b of x. So if you think about this carefully, what I've just written here is actually just not that much different from what I wrote right over here, right? So I'm just going to write out the definition of a logarithm. So by the definition of a logarithm, it must be that b to the z is equal to x, right? That's what this says, right? If I log base b of x is equal to d, then it has to be that b to the d is equal to x. So if z is equal to log base b of x, then it has to be b to the z is equal to x. Because that's the same base, right? So we have this. Now, I'm going to use a property that we had from exponents. So watch this. Then we're going to do what I just described a moment ago. This is actually why I brought this up, is that because I know that this is in fact an equation, these two sides are equal to each other. So what I'm going to do is I'm going to raise both sides of this by an exponent. Then, this then looks a little sad. Then raise both sides of the equation by exponent y. So I'm going to kind of cook up what this is for the matter of the statement. So I'm going to try to derive this statement using this much more basic definition. So here we go. So I'm going to raise both sides. So that means that x to the y has to be equal to b to the power of z raised to the power of y. But what is this? Well, because of the properties we talked about with the exponents, it's b to the z times y, right? But I'll write it as yz because the order shouldn't matter. Yz. So that means that log base b of x to the power of y is equal to log base b of b to the y times z, right? That's what it means. That's a consequence of this. Because x to the y is equal to b to the yz. So if I look at it in terms of logarithms, they should be equal. So now here we go. Now I have this. Well, log base b of b to the yz is equal to yz, right? That's what the answer is, right? Because so it's asking b to the what is equal to b to the power of yz. Well, this tells you the answer, right? It tells you it's yz. It's sitting right there inside those parentheses there. And what's yz? And yz is equal to y log base b of x, right? So y times log base b of x. Hence, well, has to be then that log base b of x to the power of y is equal to y times log base b of x. And we're done. So just to kind of recap this, we figured out that that x to the power of y, so specifically log base b of x to the power of y is equal to log base b of b to the yz. Well, when we see that, the right-hand side over there is just equal to yz, right? But we established that yz is just y times log base b of x because of the first way we defined what z is. And then lastly, since we knew that those two are equal, this has to be the case too. So for those that are just looking for a very simple way to look at this, which is effective enough, it's easy enough to remember, is you can imagine like I'm dragging the y out front, or I can even put it back in. So I can take this exponent, I can drag it out in front, or if I wanted to, I can put this back inside of here and exponentiate everything inside of the parentheses here for the logarithmic function. That's a very simple way you can use the power rule.